So our next speaker is Raphy Coifman from Yale University. And I, of course, don't know how to work the Macintosh. Oh, there we go.
Okay. Okay, it's great to be here. And let me congratulate Ingrid for being in her prime. This is a great meeting. In fact, one of the things I'd like to show is that even in the context of very general abstract data, like documents or questionnaires or databases in general, wavelets play a very critical role. And you will see this appear very quickly. So let's start with this example here, which basically will be a motivation for what I want to describe. Assume that you have a database of text documents. So to each document, you basically associate the histogram or the frequency of occurrence of various words in some lexicons that you pick. And the issue is, can you organize the documents? And many people here, like Larry and others, are using a variety of Bayesian and other methods to do this kind of organization. The point I want to make here is that you need to add some geometry into the picture. And I'll make it quite clear. So when you look at those documents, if I want to compare one document to the other in the crude way, I will just compare the list of the coordinates of the document, which are the probabilities of certain words occurring. And if the distribution of vocabulary in the two documents is very close to each other, I would assume the two documents somehow deal with the same topic. And I may build a graph or link them by just doing that. The problem with the approach, which is sort of the initial issue, is that very frequently, you could use different words to basically convey the same meaning. So you would do a much better job if you had a metric on vocabulary which basically conveys distance in meaning between the words. Okay, now that's on the one hand. On the other hand, if I wanted to organize, so I need to be able to organize vocabulary by meaning, so to speak. So how would I deal with vocabulary to organize it by meaning? I will take two words and see if in a corpus of documents, they're used in the same documents at the same time, or to what extent I can predict the occurrence of one word, knowing that the other word occurred with high frequency. So there are various ways of associating words to each other, and so defining some sort of metric about between vocabulary. The problem with that is that you're looking at individual documents, and really what you would like to say is that certain words occurred in certain topics or in certain contexts of documents, and so you need to be able to compare vocabulary by the occurrence of in not only in individual documents, but in topical groups of documents or contextual topics, if you wish. So we need, if you want to organize such a database of documents, you have this duality between the coordinates, if you wish, and the observations, which are the documents, and somehow we need to put them together. So the conventional way of doing it has been by some sort of standard metrics that you would take, either probabilistic metrics or others. The point I'm making is that we need to sort of make the metrics a little bit more plastic in nature. So some of you, perhaps all of you know that there is this metric called Earth mover distance, which incorporates which is a metric to measure the distance between two distributions or two probability measures. And it allows you to sort of match them to each other by using what is called a transport. So let me give you a one-page tutorial on Earth mover distance. So for example, you have the three histograms A, B, C up on top there, which are basically correspond to the amount of energy in the various polar rectangles over there. And the question is, which one is closer to which, right? If you were to compare histograms, so the histograms are below that, the D, C, and D are the histograms. If you were to compare the histograms directly, as you can see on the table next to it, you'll screw up. You really want to do this Earth mover distance, which means that you are allowed in the comparisons to deform each one of the histograms by moving some mass from one bin to another bin, but paying a penalty which is in terms of the distance between those two bins. And you want to basically you define the distance between histograms to be essentially the infimum over all possible transport of mass between bins. And that's a natural distance. I mean, people in image processing, you have an image, you have a distortion of the image. They match images by just taking the minimum of the distance over all possible distortions of one in order to match to the other. Let's say you do digit classification or something. So this is quite natural. The remarkable fact is this. So usually it takes, if you have n bins, if you do normal optimization, it'll be about n cubed calculations. There are literally dozens of algorithms to accelerate them out there. And one of my points here is that they're all, it turns out that many of those algorithms are actually correct. They all give you an equivalent distance. Okay, and for some reason this was not observed. In mathematics or harmonic analysis, it has been known for at least 30 or 40 years. So the reason for that is that there are two ways of computing a distance between two probability distance. One is do an optimization. The other one is doing the dual problem. When you have an optimization, you have a dual problem. And the dual problem is really the interesting part, which is what you will see on the right-hand side. You see my cursor here. The Earth mover distance the length of P in Earth mover distance, P is the difference between the two histograms, as you can see up on top, is given as a soup over all f, such that f of x minus f of y is less than, say, if the penalty of motion is a distance, it would be x minus y or x minus y to the power alpha. In other words, the Earth mover distance is the dual norm of the Holder norm or Lipschitz norm. And we have known forever how to compute that. As you know, Lipschitz functions, at least on the line or in Rn, are characterized by the fact that their wavelet coefficients are bounded once they are rescaled for the scale correctly, okay? So the dual norm is L1, right, in this case. This is all discrete. So if you want to compute the dual norm of Holder, it's just little L1 on wavelet coefficients. In other words, the norm between two probability density is computed by taking their difference, taking the wavelet coefficients, multiplying them by the opposite normalization you have for Holder, and taking the L1 norm of the sum, okay? It's an instantaneous calculation. Not only that, but as you will see in a minute, it's a calculation that really makes sense. And in fact, it's in a way much more natural than the definition of Earth mover distance. So here's just an example of doing that. So here we took an image of some military vehicle going along a path. And what you want to do is compare the distance of the different images to one baseline image at type 200 with Earth mover distance of 3 types, right? Computing it by wavelet coefficients, computing it in the usual way by optimization, and you see that they really track each other. The curve that you have here really tracks each other quite well. So in reality, this is quite good and works very nicely. Let me now deal with it more from the signal processing point of view. Let's say that you have an image. You view the image basically as a histogram of the energy that you see at every individual pixel. So the Earth mover distance, as I said, between two images would be just to take the soup over all Holder functions or Lipschitz functions. But in reality, if you look at this expression that I have here, I'm saying I have two distributions, two images. Let's say, just to make it concrete, think of the images as the images of those curves that you see here, right? So if I want to compare two curves to each other, of course, if I just take the images between the singular measures, the distance between singular measures, I get the distance is always going to be 2, which is useless, right? I want to know one curve is closer than the other, and those are singular measures. How do I compare curves, right? And the answer is you do the easiest thing in the world. You basically take the soup over all functions in some symmetric convex set. In this case, it's a unit ball in Holder class, or it could be any sensor. So you want to think of F as being sensors, and by thinking of F as being sensors, which are holders, you're thinking of them as functions which have less sensitivity in the high frequency bands than they would have in the low frequency bands. And you're discriminating between objects by basically accounting for the band of the object in doing this discrimination. Doing that, you're really sort of penalizing, if you wish, the high frequency bands, which tend to be noisy and so on. So what I'm telling you is something that everybody who has done signal processing has done all his life, in some sense, without knowing they were speaking in this language, right? But the point is, this norm is very easy to calculate, and let me just do it instead of using wavelets. Let's just discuss it in the case of an image. What it means is take an image, just blur the image by convolving with a Gaussian, then take those blurred images and integrate over the different scales by penalizing the small scales and giving more weights to the very blurry scales. And you get a distance. The definition, the way I wrote it down, is basically to tell you, well, I didn't really care that I had a Gaussian. It could be any Markov process, diffusion process, anything you wanted. You could do it just as well. And everything that works in a classical case works on any graph, if you wish, if you have a nice diffusion process on it. So you get that. Here is what happens if the collection of curves that you're taking are curves that arise from a dynamical system, like the standard map here, and you want to organize all the curves as a way of characterizing the standard map as a graph, right? This relates to what Ron was talking about before. I have a collection of manifolds. I want to organize that collection of manifolds and tell basically, as a structure that enables me to identify the full dynamical system, or to identify each individual orbit of the dynamical system. And you apply the method I just described, it works like a charm. Here is another example. You have all those curves. You want to match curve to each other. All you have to do is blur them, match the blurred version, scale it appropriately, and add them up. It's completely trivial, okay? The beauty is, of course, that you can do things very simply that seem to be not so easy to do, right? If I want to find among all those curves, which is the one that's more central than the others. It's a 1-minute calculation, okay? And the norm is basically if you view it, it's a Besov norm on the measure, right? So you take the measure, take the Besov norm. Now, what's the point? One of the main problems that we have with data is that you have data, it's distorted a little bit, take a usual metric, that metric completely separates the small distortion. So you want to be sure that what you have is plastic enough so that small distortions don't throw you away, okay? And this Earth mover type or dual metric, when you're looking at duality for smooth functions, distortions don't do very much. Because for smooth function, distortion don't do very much, in the dual space, it's the same story. That's why the whole thing works. And it has nothing to do with transport or anything. It just has to do with what is a collection of sensors you're taking to measure the disparity between two different objects. Okay, so now, it turns out, I didn't know I was speaking in prose. We were organizing databases, and because of harmonic analysis, we organize databases by using those kind of metrics all the time. We just didn't have this interpretation of it. And it works extremely well. So it does to a database. If I take a database, in this case, I'm showing you what a database is on the screen. You have to do exactly the kind of thing I discussed for documents. So here, this particular database is a questionnaire. Every column in this messy matrix is a person. Every black dot is a no answer, and every white dot is a yes answer to some question. So there are 3,000 something people, about maybe 550 questions, and you have that, you're given that. What you want to do is basically organize the population by stereotypes, as Larry would like to say, right? Which means people who respond in the same way, groups of people responding in the same way to questions. And you want to organize the questions conceptually so that you will know that if you know the answer to one, you know the answer to the other, but you want to do it in such a way that both the population and the questions would be on as smooth a structure as possible. Now, for us, smoothness is equivalent to predictability, okay? If I know what happens to my neighbors, I should know what happened to me, and the smoother it is, the more predictable it is, okay? So this would be on the level of questions and so on. So the miracle here is the one I'm going to show you in a minute, that when you take this database and you start to organize it initially by just correlating columns to each other and rows to each other, if the correlations are high enough, you build a graph based on that. On the columns, you build a graph based on that for the rows. Once you have a graph, you can build a hierarchical decomposition or a tree decomposition on the graph. I will show you that in a second. And so that allows you to organize, if you wish, a tree on the columns, a tree on the rows. And you look at this as your initial starting point to build an association between columns and columns based on Earth mover distance relative to the metric on the rows, and association between rows and rows based on Earth mover distance built on the columns. So there is a duality between the rows and the columns. There's a metric on the columns, metric on the rows. You use them both to do that. So let me show you what happens. So this messy organization that I showed you before, by the way, if I go back to the picture, you see that the one below is a little bit better organized in the sense that you see a structure in there. If you focus on one of the squares, so this is one collection of people here, and this is one collection of questions, you see that the response is a pretty clean barcode, which means that all the people in that group more or less answered the same way, okay? And that's what the barcode means. That's essentially it. So the group of people was correct, and the questions, the yes and no of the question, black or white, is sort of an artifact of the questionnaire because you can formulate every question, you know, the opposite way. It's still the same question. Right? So there's some sort of polarity floating. Okay, so here it's again, so what happened here, and you will see it in a minute when I go to the next picture, the population is organized on a very smooth two-dimensional manifold, okay? Which, by the way, when we were doing it before was not so smooth. It's a very smooth two-dimensional manifold. The different groups in the populations are different colors. The ones that highlighted dark blue here is a group of people who have a lot of psychological issues. And you see that the barcode, I mean, what you see here on top is basically in units of standard deviations, how strong their problem is. For example, this is depression, and this HS might be, I don't know, hysteria or whatever it is. It's some psychological condition. All of those people here have real trouble. On the other hand, on the other side of the spectrum, by the way, so this map, this geography of the population is such that one extreme is one extreme, and the other one is the other extreme, and you have all possible gradation in all directions of the profile. Okay, so this is a true demographic map, if you wish. If you are on the other side, so the red points here, you see that they're all way below normal in response. In other words, they are extremely healthy and stable and so on. So you could do this. By the way, this generates a tree, and the trees that we build there, we build a binary tree, so there are wavelets, in this case just Haar wavelets attached to that. And so if you wanted to compute distances or Earth-mover distances, you just take the sum of the wavelet coefficient, absolute values, scale them up. So the L1 norm plays a role. In a similar way, and this is what really surprised me, and I will, is the fact that the questions themselves are also on a two-dimensional manifold. I have no idea why. Okay, it may be lack of imagination of the psychologist, and that could only drift in two directions from one question to another. And again, the grouping are extraordinary. So can you read anything there? Yeah. So here's a list of questions. I find it hard to keep my mind on a task. I'm certainly lacking of self-confidence, and all the questions are like that. So this whole group of questions is basically lack of self-confidence. That's a meta question like that. Here's another one, which is basically, I'm almost never bothered by pains. I hardly never feel pain, and I'm not easily angered. Basically, somebody who is comfortable in his skin, right? And so this is well-being. And you see, okay, this is a picture of that manifold, and this is the same manifold sort of from another point of view, rotated around. And you see it's quite smooth, very nice structure, and quite remarkable. So somehow, again, by the way, you don't see any of that if you just do one scale of the thing without the Earth mover distance. Everything is sort of like a scatter plot out there. I mean, you still have good groupings and so on. Again, when you look at the tree, I picked a node in the tree of questions, then what I see on the top is basically the response of the different population group to that question. I'm sorry, so let me go back. Now, what has happened here, however, is not Earth mover distance. Earth mover distance was applied to the columns, applied to the rows, gave a tree, which when you have a tree, you have Haar basis on the rows, Haar basis on the column. You get basically a tensor Haar basis. And you find out that if you look at the expansion, and this process that I'm describing is iterative. In other words, I started with some initial organization. I get it better with Earth mover distance. Once it's better, I can get it even better by iterating this. And if you define the entropy of what you got to be the sum of the L1 coefficients of the double Haar expansion here, you find out that it drops incredibly rapidly by a factor of 5 or 6 or 7 from where you started off. So you really compress the data, explain the data rather nicely. I'm not going to pursue that. What one finds is that the database that seemed to be completely disorganized is actually, given any percentage that you are willing to discard, you can show that it satisfies a Byholder condition in the entries of the database in the metrics which I've defined. So let me skip all of that. It can be done without Haar basis by using basically martingale differences. And if you're familiar with that, you realize that you never need to build an orthogonal basis. You just need to have differences of expectations at different scales to do all of that. And the references are here. The theory, the general abstract theory of everything I described is a technical report. It's reference number 10. Was written just a few days ago. This whole thing came to my conscience about maybe three months ago. I didn't realize, I didn't know what Earth mover distance was. So there are people here at the meeting like Piotr Indyk, for example, who has been worked quite a bit about it. The beauty is it's incredibly fast to compute and incredibly natural from a duality point of view. So I'll stop here.
Again, I think we have time for one quick question. Hi.
Could you define the
What? Yeah.
show the integral of the string over all the functions
Yeah.
alphabet, but then you showed an example where you said, oh, it's not going to integrate over all scales. So, what I didn't understand is how did you find all this functions?
Oh.
Or the compute?
Oh, okay. Usually when you have, let's discuss a simple case. That you have I'm on the interval 0, 1, and I have a binary tree on it, and I look at Haar functions, right? Then that means that I'm comparing the averages at different scales, right? Haar function is defined by scale. I can look at Haar coefficients. I can take the absolute value of Haar coefficients, multiply them by the length of the interval in which they're supported, okay, and add that. So I have a sum for each scale, and I sum the scales from whatever my resolution is. Right? So if I had, say, 1,000 points, I'll have 10 scales. Right? So that's all there is in the calculation. If you are in the abstract case that I was describing, you have a data set. You're building a tree. Here I build a binary tree. It's usually not binary. You're building a tree. Then you could say I could just take the average on a given level of the tree. So it's a partition tree of the data. Right? So you basically take the averages or the differences of averages of a layer of the partition, multiplied by the volume of the function in the layer of the partition, and add up over the different layers. Okay. Now it turns out whether you do wavelength coefficients, you do just averages, it's equivalent. It doesn't matter provided you are applying it to differences of two probabilities which have integral 0. Okay. So there's subtle cancellation going on. You have to deal with it. Okay. Otherwise it's wrong. But as I said, the whole theory is worked out. It's very simple. It's just a translation of